In this presentation, I'm going to be covering the basics of biomechanical analysis. The primary tool that I'll be using for this presentation is BoB, Biomechanics of Bodies, a self-contained biomechanical analysis package produced by BoB-Biomechanics Limited. BoB contains a human musculoskeletal model. The body is broken down into 36 segments, and these segments are joined by 34 joints. The segments are the major components of the human body, for example, the thorax, the skull, the pelvis, the upper arm, the lower leg, the foot, the hand. These segments are then joined by the appropriate joints. The user can change the overall height and mass of the subject, or alternatively, they can go in and change the individual dimensions and inertia properties of each individual segment. BoB contains the mathematical equivalents of the various joints around the body. These are normally written in terms of constraint equations. Perhaps the simplest of these is the elbow joint, which releases 1 degree of freedom, the simple flexion-extension. More complex than the elbow joint is the hip joint. This joint releases 3 degrees of freedom, so that's flexion-extension, abduction, adduction, and internal and external rotation. The knee joint might look like a simple hinge, but it's got the slide and roll of the tibia on the end of the femur. It also has the patella sliding over the end of the femur. These are modelled in the constraint equations. More complex again is the spinal column. In BoB, all of the vertebrae in the cervical and the lumbar region are modelled, and their facet joints are represented as constraint equations. BoB is a musculoskeletal model and therefore contains representations of all of the major locomotor muscles within the body. Currently, BoB has over 600 muscle units across the whole body. The muscles can be modelled as simple force generators or 3-element Hills models. The muscles also have the ability to wrap around the underlying skeletal structure. BoB contains a muscle editor which allows the user to change the location of the muscle's origin, its insertion, and any underlying wrapping around skeletal components. In the muscle editor, you can also change the maximal isometric force that the muscle can generate, basically how strong the muscle is, its optimal fibre length, its tendon slack length, and its pronation angle. BoB uses inverse dynamics to calculate the torques at the joints throughout the body. Let's just consider initially a case of inverse statics. So we have the subject as in the diagram. We've got the pelvis connected through the lumbar spine up to the thorax, and then we'll consider one arm coming off from the shoulder, the elbow and the wrist. And the task that we want to do is to calculate the torques at all of those joints. If we know the location of the pelvis and we know the angles along the lumbar spine, we can calculate the position of the thorax. If we then know the angles at the shoulder, we can calculate the position of the elbow. And if we know the angle at the elbow, we can calculate the location of the wrist and hence the hand. So by the time we've got to the end of this chain, the kinematic chain, we know the positions of all of the masses and of all the joints. We can then work back from the hand, back towards the pelvis, calculating the torques as we go. So if we consider the wrist, we know where the force on the hand is, because we've already calculated the positions, so therefore we can calculate the torque at the wrist. We know the orientation of the forearm, so we can add on to the torque at the wrist. We can move it down to the elbow by considering the forces, probably the weight, acting on the forearm, and then we can track back to the shoulder, through the thorax and back to the pelvis. So at the end of solving this chain, we know the positions of all of the joints, all of the masses, and the torques along that kinematic chain. We'll now extend the inverse statics principle into inverse dynamics. The approach is the same of working from the root towards the tip of the limb to solve for position, but as we're now considering dynamics, we also include all the velocities and accelerations of all the joints and the masses, and those are linear rotations and accelerations and angular rotations, accelerations. In calculating the torques, we also need to calculate the inertia forces of those masses which are accelerating and undergoing angular acceleration in the calculation of the torques. But again, we start at the tip. In the case of, say, the arm, we start at the hand, calculate the torque at the wrist, then move down to the elbow, down to the shoulder, down to the thorax, and down to the pelvis, and calculating the torques at all of the joints along that kinematic chain. Let's now go on to consider the role of the muscles within the body. What do the muscles do? Well, obviously they generate movement of the body, and they do this by producing torques at the joints. These are the torques that we've just calculated in inverse dynamics. The torques are generated by the muscles contracting and pulling on one side of the joint against the other. So it's a total internal force. The muscle doesn't act straight through the centre of the joint, it's displaced from the centre of the joint, and therefore the force in the muscle is generating a torque at the joints. This situation is shown in this diagram. The red arrow is the externally applied force, although this could be due to accelerations of the body components. This force generates a torque, in this case at the elbow, indicated by the circular purple arrow. This torque is counteracted by the force in the muscle, which has been indicated by the green arrow, which runs along the line of action of the muscle. Note also, though, that the force in the muscle also contributes to increasing the joint contact force at the joint, and often the force due to the muscle can be much larger than the force due to externally applied forces. So if we want to know what the forces in all of the muscles are, it should be quite easy. We know that those muscles generate the torques at the joint, so we know what the torques at the joints are. The problem is there are many more muscles than there are torques. Typically, there will be about 600 muscles throughout the body, whereas typically for the major joints, there's only about 40 torques. Hence, there is no unique solution. Therefore, to solve for the forces in the muscles, we need to introduce certain assumptions. What we'll do is we'll assume that the body configures itself to try and reduce fatigue. It seems like a reasonable survival strategy. What this translates into is basically trying to turn off the muscles as much as possible, but while still generating the required torque that we calculated in inverse dynamics. Mathematically speaking, we can say that the sum of the activations of the muscles is going to be minimised. By activation, we mean that's the ratio between the instantaneous force generation of the muscle divided by the maximum force that the muscle can generate. So if the maximum isometric force of the muscle is, say, 1,000 newtons, and the muscle at that instant in time is generating 500 newtons, its activation is 0.5. By introducing this single assumption, it's now possible to solve for all of the muscle forces within the body, assuming that assumption is correct. Or to put it mathematically, what we are saying is we are minimizing a cost function, the cost of the body moving. A commonly used cost function is the sum of the squares of the muscle activations. Unfortunately, the force generating characteristics of human muscle is very complex, so therefore we do the only reasonable thing. We replace it with something much simpler. This is an example of replacing the complex characteristics of the muscle with something much simpler. We replace the actual muscle with a in-series tendon stiffness, some idealised contractile element, and we put an elastic element in parallel with it. This is Hill's 3-element muscle model. We can also modify the muscle force generating capabilities as a function of its active length, how much passive force is going through it, it's basically its nonlinear stiffness, and its contraction rate. All of these affect the amount of force that the muscle can generate. To use a biomechanical model that incorporates inverse dynamics, we need to be able to specify the movement patterns of the subjects. This can be done in a number of ways. Probably the most simple is just to specify what the joint angles are. So in this example, we're just saying that the knee flexes a certain amount as a function of time, probably in terms of a tabulated table. That's convenient, but doesn't happen very often in real life. To model real life applications, we probably need to use some form of motion capture. Motion capture comes in two basic forms at the moment. There's optical tracking. It's used a lot in film generation, where you have animated sequences from computer-generated graphics. To do this, they attach retroreflective markers to the subject and surround the subject with cameras. Each camera can see a 2D representation of where the markers are. So putting together a large number of cameras, for a Hollywood studio, you could be talking in terms of hundreds of cameras. You can work out the locations of all the markers. It's an upscaled version of your two eyes, basically. This is a very good method in that it gives very good accuracy in terms of 3D locations of the markers. And if you know where the markers are, you pretty much know where the body is. However, in terms of biomechanics, there are certain disadvantages of optical tracking shown on the previous slide. It's very expensive, it's cumbersome, you can't move it around much. The volumes in which you can measure is quite small, and it has great trouble working outside in terms of sunlight. The cameras can't compete with the sunshine. So therefore, what we're now tending to do is use inertial measurement units, as shown in the little orange cube in the hand on the left-hand side of the screen. Within that little sensor, you've got 3 magnetometers, you've got 3 linear accelerometers, and you've got 3 rate gyros. By synthesizing that information together, you can establish what the angle of the sensor is, and if the sensor is attached to the subject, it means you can measure what the segmental orientation is. And if you know the position of the root segment, often the pelvis, using a kinematic chain, as we described on a previous slide, you can work out the locations of all the segments of the body. So by using these IMUs, we can get out of the lab and into real-world situations. This is an example of some work we did on an outside tennis court. We're measuring the position and the movement of 2 tennis players, one of which was the novice and the other was the teaching professional. And we're considering the torques that each of them were generating during a rally. We can also move out into hostile environments. This is some work that we did with motion capture up a tree. And finally, for our biomechanical analysis, using inverse dynamics, we need to know what the external forces that are acting on the subject are. These forces typically come from 2 sources. The first is the force between the subject and the floor if they're walking or running or moving around. So that's termed the ground reaction force. This can be measured using force plates buried into the floor, or it can be calculated using BoB. If the subject is handling equipment, there's often a significant force between the equipment and the subject's hands, or whatever part of the body contacts the equipment. In that case, these external forces must also be accounted for in the biomechanical analysis. And so to summarise the analysis process, we need to know what the motion of the subject is. This can be from motion capture or specifying the joint angles. We need to know what the external forces being applied to the subject are. We also need to know characteristics of the skeleton. This is describing the mechanism within the body. So this could be in terms of segmental lengths, the locations of the joint centres, the characteristics of the joints. All of this information is fed into an inverse dynamic solver, which generates the torques at the joints. We then need to decide on a cost function, basically how the muscles are behaving, and we need to know characteristics of the muscles themselves in terms of the individual strengths, for example, of the various muscles. This is fed into an optimization process which minimizes the cost function, and from this we can generate the muscle forces and the joint contact forces. And finally, BoB can also take in synchronized videos. This doesn't form a part of the analysis procedure. It's just very handy a few days later when you're reviewing the data results, just to see exactly what the subject was doing at the time, just to check that it makes sense, to undergo sanity checks. Well, we've done a lot of work to get to this point, so basically, was it all worth it? What can we actually get out of the biomechanical analysis? So this is a few of the outputs. We can plot trajectories of anatomical locations, positions, velocities, accelerations of any point on the body. We can display segmental orientations, muscle forces, ground reaction forces, joint contact forces and torques. What we'll now do is go through that list again in a bit more detail. So firstly, anatomical trajectories. What we're displaying here are the paths of the hands and the feet. So the yellow and the red are the hand paths, and the light blue and the white are the paths that the feet take through space. In BoB, these are a part of a 3D viewer, so you can spin that round and view it from any orientation, even from under the floor, just to get an appreciation of the paths. So for example, in dance, that might be important to the choreographer to know exactly what the movement pattern of his dancers are. And we can take this approach one step further to include temporal as well as spatial information. This trajectory is shown with time markers at regular intervals along the path. So the colour changes at a regular time interval. So therefore, the longer the segment of a particular colour, it means that the faster that part of the anatomy is moving at that instant. We can also show movement in terms of instances. So these are like little photographs of the subject as they move. So in this case, we've got a fast bowler and we're taking regular snapshots of the subject as they go through their action. Again, this is in 3 dimensions, so you could rotate that and see exactly how they're moving from any particular viewpoint. The biomechanist might be interested in the range of motion of any particular joint. In this example, we're showing the range of movement in extension and flexion of the right shoulder joint, and this is indicated using the disc that is placed through the shoulder joint. In the red region, that is where the joint spends most of its time, and occasionally it goes up towards the green sections, whereas the joint never enters the blue section of the disc. The biomechanist might want to know which parts of the body are moving the fastest or the slowest and in what particular direction. To display this, we display velocity vectors actually attached to the points on the body. So in this case, we've got each hand is showing a velocity vector, the left foot is showing a velocity vector, and the head is showing a velocity vector. So we can see how fast they're all moving and in which direction. So far, we've been displaying the whole body, but sometimes you're particularly interested in a part of the body, for example, the limb or one leg in this case, in which case that individual section of the body can be displayed along with all of the muscles that are connected to that body or cross the joints associated with that part of the body. Another way to see the body motion is to attach a virtual camera to a part of the body. In this case, we've attached a virtual camera to the right femur. So as the subject moves, the right femur appears to be stationary and everything is moving around it. So you might be interested in this case, for example, the movement of the knee or the hip joint. Biomechanical analysis can be used to compare the actions of two subjects doing the same task in what looks like to be a very similar method, but there are very subtle differences which biomechanical analysis could pick up. In this case, you've got two people lifting a box and placing it on the shelf, and to the naked eye they look very similar, but if you look at the muscle activations, you can see that there are subtle differences. Also, we can plot out graphical data over on the right hand side, which again emphasises the very subtle differences between the two performances. Using motion capture means that at any time in the future you can view the action from any direction and from any angle. This also extends to viewing the action as regards to time. You can view the action faster or slower, or indeed at a variable rate depending on what the action occurring is. This means that unlike video cameras, you'll never get blurring of the movement using motion capture. You do have to ensure that the capture rate at which you're operating is suitable for the action. So if you're looking at just a human gait, for example, a capture rate of say 60 frames per second is normally adequate. Whereas if you're looking at explosive sporting action, for example golf, you'll probably need to go to a higher frame rate of say 250 frames per second or maybe even 500 frames per second. As the mass distribution around the body is known, the location of the centre of mass can be calculated from the position of the body segments, which has just been captured by motion capture. In this slide, the location of the centre of mass is indicated by the green sphere. Knowing the location of the centre of mass is useful for calculating the stability of a body, but it can also be used to calculate the ground reaction force. This is the force between the subject and the ground as they're in contact with the ground. If we know the location of the centre of mass, we can therefore calculate its acceleration. This acceleration has come about due to the external ground reaction forces, and therefore the ground reaction force can be directly calculated. During the phase where there is 2 feet in contact with the floor, the ground reaction force has got to be distributed between the 2 feet. This can be done by a consideration of the angular momentum of the body. In the slide, the ground reaction forces are indicated by the yellow arrows that are occurring at the feet. BoB can also be used to display the torques that are occurring at the joints as was calculated during the inverse dynamics phase. In this example, a subject is raising and lowering her right arm when there is a vertical downward force applied to the hand. You can see that as the arm is fully extended, there is the maximum torque occurring at the shoulder and in the lumbar region, as indicated by the circular arrows. You might also note that this changing position of external force is affecting the weight distribution between the feet, as indicated by the vertical yellow arrows. We previously discussed how to calculate the force distribution across all the muscles in the body. This slide is illustrating that calculation. Here it's a person who's involved in a tennis rally, and we've attached a virtual camera to the pelvis so we can observe the activation of the muscles in the lumbar region of the back. The muscles are colour-coded. The more red the muscle is, the harder it's working, so its activation is higher. Blue muscles are not particularly working hard at all. If we know the muscle forces in the muscles that surround a joint, we can vectorially add all of these muscle forces together with the force of constraint to generate the total contact force across the bones at any particular joint within the body. In this example, the joint contact force is indicated by the double-headed arrow at the right hand elbow. We've been displaying a lot of results from a biomechanical analysis in the form of animated skeletons and avatars, but of course all of this is backed up with real hard numeric data, and all of this can be dumped out in terms of plots or in terms of tabulated data. Over towards the right hand side there is plots of joint contact forces, which is synchronized via the moving cursor to the animated skeleton. All of the plots that we've seen so far are of variables plotted against time, but within BoB we can plot any variable against any other variable. In the graph over towards the right hand side of this illustration, we're plotting the elbow torque against the elbow angle. The moment in time is indicated by the little dot that is moving around the locus of the graph. BoB can also synchronize human movement to EMG recordings of muscle activities. In this illustration, we've got somebody on a stationary bicycle and they have a number of EMG sensors attached to their legs. The signals that are being generated by these sensors is shown over towards the right hand side of the screen. The colour coding on the moving skeleton is now not the calculated muscle activation from inverse dynamics and optimization, but rather the colour coding is based on the root mean squared muscle activation that has been measured by the EMG sensors. MATLAB is a widely used mathematical modelling environment. It's especially used within engineering and scientific analysis. BoB has been developed within the MATLAB environment and therefore inherits much of the functionality of MATLAB. It also means that files can be readily shared between BoB and MATLAB. It also enables MATLAB users to write their own bespoke code that interact with BoB, and it enables MATLAB users to use the advanced graphics of MATLAB. This is an example where we've been using MATLAB graphics to produce animations of ancillary equipment. BoB is accredited by the MathWorks Connections program. What I'd now like to do is provide a few examples of biomechanical analysis actually being used. Biomechanical analysis has been widely used in sport. In fact, we've seen a few examples in the presentation so far. By using biomechanical analysis, it provides a deeper understanding of the mechanism of any particular sport. This provides the analyst, the athlete, and the coach with objective quantifiable data on the athlete's performance. This data has been used to optimize performance and identify features which reduce competitiveness and eliminate them. It can also be used to compare the action of athletes at different levels so that a less experienced athlete can learn from their more experienced colleague. Closely related to sports analysis is dance analysis, but not for choreography, but to reduce dance injuries. BoB is being used by a professional Irish dance company who were concerned about the injuries to their dancers, especially in the ankle region, which was occurring with an alarming regularity. Using BoB, they calculated the loads that were occurring at the ankles during particular dance steps. The one in the illustration is called the rock. This is where the ankles are moved from side to side whilst being full load bearing. This action is stabilised by the surrounding muscles. What was found was that very large forces were occurring at the ankles of the order of 10 times body weight or more. What the choreographer did was, using this information, they slightly changed the motion pattern of the dancers, not so much that the audience would recognise it or even notice it, but it was sufficient to substantially reduce the loads that were occurring at the ankles, and the injury rates reduced as well. Another application of biomechanical analysis is in vehicle design. In this study, the automotive manufacturer was interested in increasing the ease of use of vehicles for the older person. You can see the subject has got the little orange IMU boxes attached to them so that they can be measured as they get in, sit, and get out of the vehicle. This information was then fed into a biomechanical model. In this case it was BoB, which was used to calculate the loads that were occurring during ingress and egress. Using this information, the vehicle manufacturer was able to optimise the interior design of the vehicle to increase the comfort of use for both the driver and the passenger. Many of you will be familiar with the Formula One pit stop. The car enters the pit. The crew then has to change the wheels before releasing the car. In each corner of the car, there's a team of 3 who are to change one wheel. The team of 3 consists of a person that unscrews the wheel nut. There's then a team member that removes the wheel. There's another member of the team that then puts on the new wheel, and then the guy with the wheel gun nut tightens up the wheel nut and the car goes. So in each corner, for each wheel, there are 3 men working. The objective of a biomechanical analysis is trying to reduce the time taken as much as possible. At the moment, it takes about 2 seconds to change all 4 wheels on a Formula One car, but if they can reduce that by a fraction of a second, it's worth millions to them. Therefore, what was done is each member of the team, so that's 12 in total, 3 on each corner of the wheel, was fitted with an IMU-based motion capture set, and we recorded the movements of those team members. The objective was to find out which technique for these team members was the most effective, was the fastest. So we measured all of them. What we can then do is look at the 4 corners for each individual action. So this is the wheel off, the guy that's going to remove the old wheel from the corner of the car, and we can see how they're doing. We then did the same for the person that removes the wheel nut and then tightens it up again after the wheel has been changed. And the third member of the team is the guy that puts the new wheel on. Using this technique, we were able to identify what the best method is for changing over the wheels of the Formula One team. The origin of biomechanical analysis is within a clinical environment, typically within gait analysis laboratories within major hospitals. These laboratories are used to assess the movement of patients with certain pathologies, for example, cerebral palsy, muscular dystrophy, stroke, and others. Based on the results from the motion analysis, therapies, interventions, surgery can be prescribed in order to assist with locomotion. Furthermore, the subject then can be brought back to the motion analysis laboratory and reassess to establish the efficacy of any intervention that has been prescribed. Biomechanical analysis is widely used within the field of ergonomic quantitative analysis. It provides a tool for the analysts to assess objectively the efficiency and injury risk of any particular task within a working environment. It also enables the analyst to optimize the layout of a working environment. The advantages of biomechanical analysis is that it allows direct comparisons of various tasks and individuals in respect to the potential injury risks and efficiency. It also provides a continuous means of analysis. Traditionally, just discrete actions and positions and postures were assessed, but using biomechanical analysis, it means it can be run throughout the task and no event is missed. But potentially the most important advance is in terms of sensitivity. What the analyst can do using biomechanical analysis is to find out the sensitivity to small changes of the working environment and how that affects the ergonomic assessment metrics to improve the overall environment for the workers. BoB is widely used in the study of gerontology, where the loads on the body are particularly important, especially for the more frail person. Therefore, using biomechanical analysis, it's possible to calculate the internal loads and torques that are occurring and ensure that they do not exceed the threshold that the body can withstand. Biomechanical analysis has been used by the fire service in regards to the extraction of vehicles after vehicle crashes. What they're particularly interested in is reducing the risk of any damage to the spinal cord as the subject is removed by various techniques. Therefore, in this study, motion analysis units, IMUs, were attached to subjects during extrication, and in using these it was possible to measure the position of the body with particular interest of the cervical and lumbar regions of the spine. This illustration shows the results of one of the studies where the subject is being extracted from a crash vehicle after the roof has been cut off. What we're particularly interested in is measuring the movements and the translations of the spine in the cervical and the lumbar region throughout this particular technique. This was then compared to other techniques that the fire service might use. And therefore, in summary, BoB is a biomechanical analysis containing a musculoskeletal model. BoB can import motion from joint time histories and from motion capture equipment. BoB uses inverse dynamic techniques to calculate the force and torque distribution across the whole body. BoB uses muscle optimization methods to calculate the forces in the muscles and the joints. And biomechanical analysis has many applications, including medical, product development, vehicle design, and sports performance, and many others. You can see much more information about BoB on our website, bob-biomechanics.com.